numbers tend to prove that as well, where you get a much more moderate relationship if you point-wise compare your FSI and CFD. And finally, you want to look at something called as a similarity index. And the reason for that is regions of low time average wall shear stress and regions of high TSVI are known to co-locate with wall thickening. And we've just discussed that wall thickening is one of the signs of growth and remodeling, which means that the regions that are exposed to really low values of time average wall shear stress and really high values of TSVI, these regions are prone to wall thickening. So we want to see which metric, which simulation method is really useful, and if you actually compute what is called as the similarity index, which gives you the degree of overlap between your FSI and CFD values, then you can see that the time average wall shear stress has a pretty good similarity index. So to understand the similarity index, SA here stands for your surface area. So we compute the surface area of each of them and find out to what extent they're actually co-locating. And a similarity index of 1 would mean a perfect spatial overlap, which means all of them are perfectly aligned with each other. And a similarity index of 0 would mean there is no spatial overlap. So we get a high spatial overlap between FSI and CFD for time average wall shear stress, and for TSVI we get a pretty moderate and a poor spatial overlap. And you can see that this behavior can be seen for all sheet models. Most of the results I showed was for sheet 1, and all models in this particular study tend to have pretty similar behavior. So in conclusion, we can say that the pulmonary autografts, despite having these large displacements, these traditional or canonical matrices provide a strong correlation between FSI and CFD, and not so much for your non-canonical metrics. And to ask ourselves and challenge the fundamental notion, is FSI really necessary in this situation? If you're using time average wall shear stress and oscillatory shear index as your driver for growth and remodeling, then a CFD simulation is sufficient. But if you're using TSVI or topological shear, then probably an FSI approach is much more warranted. And then this brings us to a second unrelated or distinct scenario where we try to study the biomechanical insights into aortic dissections using these fluid-solid interaction simulations. Keep in mind that these two are no way related to each other, they're just two very distinct scenarios. And we first try to understand what aortic dissections are. And dissections typically are caused when there is a small tear, one or more tear, in the intimomedial layer. Remember we spoke about the intima and the media. So this means that blood, which is supposed to flow through here, called the true lumen, actually goes into something called as the false lumen, or a false channel that is created because of this tear. And these are surrounded and differentiated with the help of a very thin flexible membrane called as the intimal flap. So these aortic dissections, they have multiple types. We're going to be using the Stanford classification in our particular study, and we're going to be focusing only on type B aortic dissections. Type A dissections occur mostly or they originate from the ascending portion. It's usually where the tear originates. It originates from the ascending aortic section, and type B dissections, they tend to occur mostly in the descending portion after this particular artery over here. So we'll be focusing primarily on type B aortic dissections in this case. And we can also see that the studies from a previous study that growth and remodeling tends to happen in pulmonary autografts. And this is also the same case in aortic dissections, and it happens quite fast actually in dissections. Within the first 14 days, the dissection transitions from something called as an acute. In your acute dissection, your flap is more elastin dominant, it's extremely mobile, and it transitions into something called subacute, and eventually it transitions to something called chronic. And you can see in the simulation here from one of our colleagues, the dissection, the intimal flap, which is shown over here, this is a sliced section of the dissection. the internal flap, which is shown over here, it tends to straighten, it becomes a bit thicker, and you have more collagen deposition and reduced elastin content over here, which means that the flap tends to become less mobile or motile over time. And this particular process is an example, a good example of growth and remodeling. And that brings us to the rationale of what do we want to study in this particular case when we already know that there is growth and remodeling. If you remember, in the descending portion of the aorta, we said that there were numerous arteries that branch out, but what we didn't, or what wasn't very visual, are there are a lot of really small side branches, really small arteries that emanate, as you can see over here, and they can either emanate from the true or the false lumen. But we had an imaging study from our research group a while back, and it said that these side branches, they're quite important, and they really affect false lumen patency opening. So consistent flow through these side branches would mean that there's blood that's constantly flowing, and which means that the false lumen will not clot or thrombose. So these side branches play a very important role in aortic dissections, and they're actually not studied at all, because around 7 to 21% of your total aortic flow or your cardiac output tends to go through these branches, which means that's quite a significant chunk which goes through them. But because they're so small, they're not really easy to visualize or scan or measure your flow data. So while there have been some studies that look into the patency and long-term growth with the presence of these side branches, the pressure buildup, which is very important in these side branches, in the false lumen with the presence of these side branches, has not been studied, and that's precisely what we're interested in. So we want to develop a fluid-solid interaction simulation or a computational model to study the pressure buildup in the false lumen with the presence of these side branches. So how do we do that? This will give you a visual representation of what the model we build would look like. This is a scan of an aortic dissection. The one in yellow is your false lumen, and the one in red is your true lumen. And we build what is called as an idealized model, or a model, because we did not use an in vivo model like our previous study. We wanted to build an ideal model to study different parameters. Each of them have their own benefits and uses. So this is what an ideal model of an aortic dissection would look like. And keep in mind, we don't have any side branches in this case. This is just a representative example. And I'm going to tell you how exactly we achieve this. We take the healthy portion of the descending aorta, and we get it's totally 240 millimeters long, which is quite long, and we take these reference values from literature. So right now we have just a straight tube which represents your descending aorta, and then you see these particular tears over here. These are the tears that tend to occur. This is the primary tear and the secondary tear, and we apply a diastolic pressure throughout, or a pressure of 80 millimeters of mercury throughout. And what we actually find over here is it's probably a visual representation of how the disease might actually occur, where the intimal flap, which is over here, is releasing to create the false channel, as you can see, or the false lumen. So blood will flow here into the false lumen and flow back into the true lumen this way. So this is what we tend to do. We apply diastolic pressure to actually create this particular configuration from a straight tube, and in the process, we remember how we spoke about pre-stressed configurations. We find out the initial stresses which are present in this particular geometry as well. So now we have our CSM model ready, but not quite, because if you see those scans, you have quite a bit of organs and the spine, which is probably surrounding it in its vicinity. So we take the effect of the spine and all the surrounding organs using a set of springs which connect them, and these values are taken from literature, and now we have a final structural or a CSM model ready. And then the surrounding, or the inside region, we fill them up with fluid elements similar to our previous study, and again we use an inflow profile and a Windkessel boundary condition as we've previously discussed. This inflow profile is of course not measured because we don't really have any scans in this case, so we actually take this data from literature. So we now have a fluid model ready as well. And again, we couple them using the open source tool Coconut, so to get a partition, strongly coupled fluid structure interaction simulation. And then the case that I just showed you right now, it's for a case with no side branches, and then we add these side branches. We don't typically take them as long arteries, but we just take them as a really small opening, which would probably roughly represent the same purpose. And we have one side branch in the false lumen, and then you have one side branch in the true lumen, and then you have one side branch in the false lumen, but you only have one single tear. And this tends to occur usually when one of these tears get occluded because of clotting or thrombosis, or sometimes you tend to have just one tear. So these 4 cases in total will give us a good idea on the location of the side branch and the presence of a side branch, on what pressure will be developed inside here. And after 3 or 4 cardiac cycles, we compute the pressures and other parameters of interest in 11 equidistant planes, and they're like 20 millimeters apart. And as you can see, each cardiac cycle takes 24 hours, so it's quite a cumbersome calculation, which means you need to be quite judicious on how many number of cycles you tend to simulate. And first we'll look at displacement, which is happening. And I've mentioned how acute dissections tend to be quite mobile, so we see a seesaw-like pattern, as you can see in the systolic phase, and then eventually the flap tends to straighten. These are really high displacements. Most simulations for FSI simulations of aortic dissections, they barely cross a few millimeters of displacement. So this is pretty high displacement which we obtain, and I'm just going to show it to you again. As flow enters from the primary entry tear, you have this really distinctive seesaw-like pattern. And if you actually look at cross-sectional view for a plane over here, the total displacement that you obtain at plane P3 would be around 8 millimeters, which is quite high. And this is a case with no side branch, and the case with no side branch tends to have the highest displacement among all cases. And if you closely look at how the configuration would look like in diastole and systole, it matches what configuration you might probably see, which is observed in vivo, so which is quite nice. So despite this being a very ideal model, we seem to get some flap displacements and flap motion, which is quite in line with what we probably observe physiologically, which is a good sign. And because of these really high displacements, you get some pretty complex flow features. This is of course with a side branch, and it is mostly marked by an entry jet and an exit jet and then a re-entry jet. So because of the seesaw motion, this continues throughout the cardiac cycle, and then eventually as the flow becomes diastolic or flattens out, the entire configuration tends to be a bit more stable, and you can see these complex vortex Dean vortices or vortex flow features that surround the primary jet over here. One parameter of interest which I would like to discuss would be the false lumen ejection fraction, because this is really strongly associated or correlated with growth. What false lumen ejection fraction represents is, let's say you have a tear, the amount of flow that exits the tear in your diastolic phase, which is represented in blue, and the amount of flow that enters the tear in your systolic phase. And this is indirectly a representation of your false lumen pressure. So a really high false lumen ejection fraction means that you have pretty good pressurization in your false lumen. And this is a very strong correlation with aortic growth. As you can see, this is mostly for chronic dissections, but it's associated with strong aortic growth. And if we compute the false lumen ejection fraction for our cases, NSB represents the case with no side branch. So when you have a side branch in the false lumen, in these two cases, you get a much lower false lumen ejection fraction compared to when there is no side branch in the false lumen. So the presence of a side branch, because there is persistent flow through the side branches, you have lesser flow that comes out through the tear, which means you have a lower false lumen ejection fraction, and you can say that this probably affects the pressurization of the false lumen as well. So the presence of a side branch probably affects the pressurization in your false lumen as well. However, I've just mentioned that the presence of a side branch affects the pressurization, but if you compare the pressures as such between the true and the false lumen, the one in red is the one for your no side branch. So what would you intuitively expect? If you have a tube and you poke a hole, you would expect to be some pressure relief. But this data says that in the presence of a side branch, you actually have an increased systolic pressure with some marginal changes downstream. It's a little counterintuitive if you think about it for a second. And we thought about as to why this might occur, and we'll probably get into it in a bit. And you see a similar behavior across all planes as well. So you see as flow enters from your right and exits to your left, the pressure for all the cases with side branches is much higher than the case with no side branches. And you see this particular pattern over here, it's called your dichrotic notch, and this dampens as you go further downstream, and this is probably because of your Bin-Kessel boundary condition. But again, increase in pressure when you have a side branch, which is confusing. So to understand why there might be an increase in pressure, we actually compared the cases case of a dissection with a healthy case. So we just remove the dissection and we just take a straight tube. So now you have a healthy aorta, so to speak, and you're comparing it with a dissected aorta. This will probably give us an idea as to why we have an increased pressure, because the case with no dissection tends to have a much lower pressure than a case with a dissection. So overall, there is an increase in pressure when there is a dissection compared to when there is a no dissection. So the dissection in itself probably plays a role in this case, because we're using exactly the same conditions. The only thing that changes is the presence of a dissection. And to understand that, we need to understand the last concept, which I'll probably explain, which is the concept of backward and forward waves. So if you have a pressure signal, such as this, you can decompose this into a forward component as your flow propagates, and if your flow has an obstruction, part of that is reflected, and that could be your backward component. So you have each pressure wave can be broken down into a forward and a backward wave. And if we break down the forward and the backward waves for our cases, the one in dark red and dark black, they represent the total pressure or the measured pressure signal, and you break them down into your forward and your backward components. So the forward and the backward components in diastolic phase, they're quite similar, and there are some distinctive changes over here because of the dissection. And the reason for that is, you remember this seesaw pattern which we saw? We see that there is an increased backward pressure over here compared to the case with no dissection, because as flow enters this way and your pressure wave is traveling, it is reflected back immediately, which means within the first 0.2 seconds over here, you have an increased backward pressure. And if you add these components together, that will probably give you the total pressure increase. So it's not just the boundary conditions, but also the wave reflection and the seesaw motion of this dissection, which is probably causing it. So now that we have some side branches as well, if you take an example of a side branch, that will add some additional reflections. So we postulate that this increase in pressure which we observe is probably because of these wave reflections that happen because of the flap motion. And to quickly conclude, you can say that the inclusion of a side branch affects the hemodynamics beyond just change in velocity, and when you maintain a constant resistance throughout your entire domain, we see that the presence of a side branch increases your pressure, especially in the systole, compared to the case with no side branch. And the Folsom ejection fraction, which, as I mentioned, is an indicator of pressurization, it reduces when there are side branches present. But of course, this is an idealized model, so you need to translate this into something a bit more patient-specific to understand if these results are well-founded. And on that note, I'm going to give some final thoughts or some final, let's say, points you can take into consideration. So we studied two very distinct, unrelated scenarios where we tried to find out metrics, namely wall shear stress and pressure, which are known to affect growth and remodeling, and we evaluated them using fluid-solid interaction simulations. Of course, the next step would be to translate them into a longer model or a fluid-solid growth model where you actually run these FSI simulations, transfer them into a growth and remodeling framework, because the growth and remodeling framework takes on for years and months, and the simulations we showed are for a few seconds. So you're mapping these small changes into larger, long changes. So this approach is actually called as small on large. So we have to probably run these simulations first, then grow the model, let's say for a few months, weeks, years, etc. Rerun the simulation and iteratively look how these parameters probably will affect growth and remodeling. And on that note, I'm gonna take your leave, or I'm much more open for questions, honestly. So thank you very much for your attention. The floor is yours. Thank you.
Thank you, Mr. Balasubramania, for your nice and very didactic presentation. We now come to the second part of this examination, the questioning of the candidate. As I told you in my introduction, our candidate was already questioned in depth during a private meeting with the members of the board, but also today, as this is an examination, there is room for questioning, of course. So, Professor Redelli, may I invite you to question our candidate, please?
Of course, thank you very much. First, let me congratulate with the candidate for the amazing work he did in these 3 years or more, and for the clarity of his dissertation and also his lecture, I would call it like that today. Very clear and elegant. And then I have a couple of, let's say, philosophical general questions that I would like to pose just to have your vision of what is going to happen in this field in the future. And I would like to start talking about pulmonary autograph. And you demonstrated, again, elegantly, how FSI is, how FSI is necessary, especially if you want to use non-conventional biomarkers like the similarity index or the TSBI.
Yeah.
So I wonder what is still to be done in order to obtain a real digital twin that can support the surgeon in its decision-making process. I mean, what are the data? What is the protocol that you envision to do that?
So if I understand your question correctly, what is missing in the puzzle to translate it into a final clinical setting?
Yeah.
But firstly, translation to humans is probably the first step. Of course, large animal models are reliable, but let's say simulation which would probably be firstly that takes the aortic valve into account would be interesting. Valve dynamics are of course much more complex. Secondly, yeah, I would say growth and remodeling wise, these simulations are probably, usually there's a 10-year follow-up on these pulmonary autografts. So a much more longer growth and remodeling simulation is certainly more challenging. Obtaining these parameters is of course much more challenging, especially if you're translating it into a human. So I'm giving you examples of how this would actually translate into a clinic. So that's why I'm taking human examples. I would say the primary challenge would be to determine these parameters for growth and remodeling, long-term growth and remodeling. Obtaining flow data is a bit easier. I think determining these parameters is probably a bit more trickier. So I would say that's the fundamental challenge. And of course, on a larger scale, there's always a computational challenge if you're considering growth and remodeling. But we're slowly addressing that over time. But I would say in terms of in this study specifically, I would say determining the parameters probably for growth and remodeling would be the trickiest one.
Okay, thank you. Just another question. You mentioned the parameters. I mean, your model rely actually on a number of parameters, even before going to the growth and remodeling part. I'm thinking about boundary condition, about material properties, about pre-stress calculations on. Not always these parameters are available, even if you ask them to the clinician. So this make your results somehow uncertain. How can you manage this uncertainty? What are the measures that you can undertake to circumvent, limit their negative effect, or maximize the effect of your model?
I think in the last chapter we've discussed about something called uncertainty quantification. It's something we've done before in our lab as well. So I would say these uncertainty quantification, especially on these material parameters, it would certainly be beneficial. There's also uncertainty in let's say the flow profile, especially in the dissection study. So I would say an uncertainty quantification study on probably the various flow profiles which can be used can also be done. So I would say to get a much more concrete understanding of the parameters, you probably would have to do one of those UQ studies, if I'm not mistaken.
Thank you. I have no other questions.
Okay, thank you, Professor Redali. And I come to Dr. Girola. May we have your questions, please?
Certainly. Good afternoon, everyone. Let me know if you cannot hear me. So first of all, Mr. Balasubramania, I would like to congratulate with you. So on my side,
Thank you.
I very much enjoyed reading your thesis and the presentation today. The lecture today was very clear and very comprehensive. So congratulations also on that.
Thank you.
I think the value of your work is undeniable, and it's also supported by the fact that you published most of your thesis already, so congratulations also on that. I have a couple of questions to help me and the audience better understand the broader application of the models you have developed.
Okay.
So the first question is about the value of your model and what can be done with your model so towards growth and remodeling. So do you envision this being more something that goes into the clinic to predict at the patient-specific level the effect of a procedure, do you see this going more towards, preclinical stage? What is your vision about the models you are developing?
I mean, the goal is to go towards a clinical stage, but how possible it is, that's of course the challenge. By preclinical stage, I assume you mean something before translation into a clinic, and that's probably where we might be, or where we might envision to be at this moment. There are way too many uncertain parameters. Idealized nature of the model, which we've discussed. Large animal model before translating into a human. So before we even address the parameters regarding the simulation, we need to address these parameters first and translate them into, let's say, a more realistic setting. So I would say a preclinical stage is probably where we would be at this point. I don't know if that probably answered your question.
Yeah, I was also looking towards what do you think is the impact you can have at, for instance, now at preclinical stage with your models?
I would say in the pulmonary autograft study, before you can run a growth and remodeling simulation, you can find out regions which might be prone to wall thickening, and then you can verify them, of course, over long-term imaging studies, just to see if you don't want the computational expense of a growth and remodeling simulation, which we just showed with the similarity index, for example. With the autograft, I would say the autograft would be more interesting because you really push the community to actually take the impact of side branches into consideration. So rather than preclinical setting, I think it's a much more impact in terms of a standard modeling approach that the community can actually take by considering these side branches, which very handful of studies actually do, and some of them do it implicitly rather than explicitly. So I would say the impact of the dissection study is more in terms of standard simulation practice in the community rather than practice within or a preclinical impact, so to speak.
Thank you. I have a follow-up second question, and it's actually a follow-up question to the question of Professor Rodelli. You mentioned that, of course, amongst all the variables that need to be still assessed is the choice of actual parameters to be used eventually for growth and remodeling.
Yes.
Which of course is still up for debate in the community.
Yes.
So I don't expect you to have an answer on which one to pick, but I would like your opinion on which ones you personally think, based also on your research, might be the way to go.
For a fluid solid growth and remodeling, I mean, wall shear stress has been talked about for 20 years now, and it's been talked about in a lot of studies. It's been shown to affect, it's been known to be a very effective disease marker or a biomarker. So I would say considering wall shear stress would be interesting. Now the parameter, which parameter to decide on the wall shear stress, I think you can begin with the more canonical parameters before you delve into something a bit more non-canonical. So I'm strictly speaking in terms of a fluid solid growth and remodeling framework. I hope that answered your question.
Yes, thank you.
Okay.
I have no further questions.
Okay, thank you, Dr. Pirola. Professor Melny, please.
Thank you. Also, on my turn, congratulations. Very clear presentation. I really enjoyed it. As you know, I'm not into the field of biomechanics or biomechanical engineering at all, so forgive me probably my stupid questions, although I was always told there are no stupid questions. So, I hear so many times, and I read so many times, growth and remodeling, that for the people outside your field, growth sounds to me like wall thickness may change over the course of time.
Yes.
Material characteristics may change over the course of time. So what is still not clear to me is that the tremendous complexity I can imagine that is involved into using your very complex tools that you developed in combination with those uncertainties. Because I can imagine there is a whole literature of people telling you in which sense the growth takes place, in which sense the material characteristic changed. But I doubt that it's exact science, right? So, how does it add to the uncertainty on your predictions?
Think a bit about this.
Because in your work,
Yeah.
you used known characteristics
Mhm.
of materials, for instance, because either they were measured,
Yes.
or you take them from the literature, and then I assume they're also measured somewhere, I guess.
You mean the
That-
inflow and the outflow? You mean, or
Or the wall characteristics,
The wall characteristics, yes.
anisotropic parameter model,
yeah,
etc.
yeah.
So, but again, as a non-expert, I assume that growth and remodeling studies implies that somebody tells you how these things vary in time.
Yes. This, I think during the private defense as well, we mentioned that determining these parameters is probably the biggest challenge that we have. Most of these are taken, as you say, from literature. For example, the actual stretch is taken as a constant, the stretch. Most of these tend to be derived from experimental values, the material parameters, but the growth and remodeling, no, I don't really have a good answer for you as to how they're actually, or what uncertainty, or how that could affect the uncertainty. I really don't have a good answer. I apologize.
Then, going back more to the field I'm supposed to know a little bit of, the fluid mechanics. When I saw on slide 84 those entry jets, exit jets, and all the vortices it creates, I wonder how come you seem to use laminar flow equations, at least that were the ones that appeared on your slide 15.
Yeah.
What about turbulence?
Yeah, we computed, as you read, we computed something called as a critical Reynolds number, just to determine if the flow is actually laminar or turbulent, and we also checked the range with which the original study proposed the critical Reynolds number, and we found that our peak Reynolds number was much lower than this critical Reynolds number. Most arterial flows can be transitional, but because it was below that, we just assumed a laminar flow assumption. There are aortic dissection studies that take turbulence into account, which is of course, as I mentioned, one of the answers, the uncertainty in the inflow profiles. It's possible that the inflow is much higher than what we've considered. So there are instances where probably you would have to take the turbulence effects into consideration, but for this particular flow profile, which we had, which is much more ideal one, we took a laminar flow assumption.
Let me be clear, I'm impressed by the complexity of your work.
Thank you.
I mean, I fully admire it. Nevertheless, I wonder, again, as a non-expert, your topics are what they are, right? But lower complex models, I guess, and I read them in your references, they exist, people studying fluid structure interaction in a non-human environment, let's say, using plastic pipes and the like. But between that level of simplicity, however complex that can be, I can imagine, but between the level of playing with plastic pipes and the complexity of sheep or humans, does your content of your work, does it imply that all the intermediate levels of complexity they have already been covered before in the literature? There is no need at all anymore to do one or two steps back and focus on simplistic engineering type models of fluid structure interaction?
I think there's been extensive literature that's covered on, by simplistic I assume you mean geometrically simplistic
Yes,
firstly.
yeah, and also material characteristic
material
wise,
characteristic simplicity.
anisotropic, etc.
material characteristic simplicity has definitely been covered extensively using fluid solid interaction. There have been studies that compare a linear elastic with, let's say, a hyperelastic material to see how, with the fluid structure interaction approach. They've been done for simple geometries, they've also been done for complex geometries, which is why when I actually compiled a list of studies, I started from a much more ideal study to see like what ideal studies have been done first and then go into much more patient-specific studies. So I think there's been fairly extensive coverage in literature regarding these aspects in terms of complexity, geometrically and material characteristically, so speaking.
Thank you.
Okay, thank you. Mars, please.
Amit, I already congratulated you with this work, which is very highly complex. So
Thank you.
very nicely done, and also the presentation was very clear to me, but I think it was also very clear to a non-expert, which is not easy to do. So well done. My first question would be, in both of your applications, you had some form of validation, which was maybe quite limited, I would say. Would there be ways to still improve the credibility of your models? Like, which data could you use?
Well, we don't really have a validation per se for the individual study, but if I understand your question, the credibility, it's only possible once you translate it into a much more, so in the pulmonary autograph, maybe a much more complex environment. And for a dissection, definitely for a patient-specific study, that's the only way I think you can find out the credibility. Especially in dissections, we see an increase in pressure, and we'd really like to see if such a pressure increase would happen in a more patient-specific case. And that's probably the only way you can test the credibility of that particular metric. For the pulmonary autografts, I think right now, I think a more extensive cine comparison would have been nicer to see if the extent of displacement which we obtained is correct, or if we're over or under predicting. But for dissections, for sure, I think translation into a patient-specific setup would be the only way to test the credibility of the study.
And then maybe a bit more philosophical. During your PhD, did you learn something that would be very important to pass on to someone who is continuing to work, or maybe
Say
something maybe you spend a lot of time on that retrospectively you think I should have learned this or this?
Oh, those are many instances. Say, maybe cliche, I would just say patience, because these simulations to set them up can be quite cumbersome. You have to wait in line and queue for this to actually run, and once they actually run, you realize you have a bunch of nonsense sometimes, and then you need to find out if you're actually making sense. And it's a very long, say, it tests your patience to the maximum degree. I would say patience is something. I can list many more, but I would say that's on top of the list at this point.
Thank you.
Okay, thank you, Dr. Mars. I'll come to the supervisors. Professor De Groot, do you have questions for your candidate?
I don't have questions anymore. I would only like to thank you for your work and your patience. Congratulate you with the presentation today.
Thank you.
Good. Mr. Sayers?
No questions.
Okay. Any more questions with the members of the board? If not, then I address to the audience. I first address to the people that taking part in this meeting electronically. If there is someone of you who has a question for a candidate, please switch on your mic and ask your question, please. no questions from the electronic part, so then I'll address to the audience in the room.
Sorry, one very quick comment. This is Anirudh Rao from Imperial College. Just want to say, Amit, well done on your thesis and your presentation. Very hard work. One quick comment. Have you thought about machine learning, incorporating machine learning or some sort of neural network for rapid prediction of your metrics, or any sort of lower order modeling?
The first technique that comes to my mind are pins, because they've been used to predict wall shear stresses with very sparse data. So I would say physics-informed neural networks is a nice next step, but I must confess I really haven't ventured much into it, but it's certainly something that's gone into the future work of my book. But other than that, it's at a stage where I'm, let's say, thinking it's something should be done, but nothing more than that.
All right, very well done.
Thank you.
Okay, I apparently was too fast. So are there more questions from the people that take part electronically? Then I address to the people in the room. Is there someone who has a question for a candidate? No? Everything was clear? And I invite
Yes, please.
Oh, yeah.
Coupling of the two codes was a very, again, patience requiring task. And I was wondering for maybe future reference if someone else is to use two different codes and couple them together, do you think, what should their ideal strategy be? Would you push them to code something themselves, or would you want them to learn to code programming as a strategy?
The documentation is actually quite extensive now for coconuts, if I'm not mistaken, and I think there's sufficient expertise to set sufficient examples to set up a case on your own. With at least I tried to learn most of it by looking at the documentation. I think it turned out okay. So I would say for now the documentation is good enough. Some modifications, of course, as per your liking, but also looking at the face of someone who's probably going to continue this work, and he has a smile on his face, which means so far it's going okay for him as well. So I would say that the documentation is good enough. Good.
More questions?
Hello.
Yes, is there someone else who has a question?
Hello. Hi, this is Abhishek. Can you hear me?
Yep. Hi.
Hi. Very nice presentation and a lot of extensive work with volunteer PhD. I had a quick input or maybe suggestion. Have you considered using resolvent analysis or transient growth analysis to maybe see which structures in your flow affect the output? I mean, which modes in your flow affect the wall shear stress the most, so you can only concentrate on those particular zones or those particular locations specifically.
You mean something like a principal component analysis, something like that?
Yeah, that's a further extension of that. Maybe use that and maybe use some. So maybe you could do it in your future work.
No, we did not consider taking specific modes into consideration. I'll have to think of how I'd have to begin working towards that, but no, we did not take that into consideration.
Because your wall is dynamically moving, so it will introduce extra dynamics. So it might be interesting to see how doing that study could maybe potentially lead to some more physical insights on what is happening in the art.
Yeah. No, we certainly didn't think of that. Probably it would be useful for wall shear stresses in the
Thank you.
Thank you.
me. To see whether there are more questions. If not, then I invite the members of the board to follow me for the deliberation. So Professor Redelli and Dr. Pirola, may I also ask you to switch to the other meeting room for the deliberation, please, where we will meet in